I'm Abby Langford. I am the chair of the community board here. Murray's a groundwater scientist who's been appointed as an independent reviewer as part of the Water Conservation Order. Murray's a senior science leader at ESR and has led research into groundwater contamination for the last 45 years. He has led multi-agency research teams focusing on the transport and fate of a comprehensive range of contaminants in New Zealand groundwater systems, including pesticides, heavy metals, microbes and nitrates. He's developed a new method for investigating the Vado zone. He was elected a Fellow of the Royal Society of New Zealand Te Apārangi in 2023. His current research interests include the impacts of land use of groundwater quality, removal of nitrates from shallow groundwater, using enhanced denitrification and the understanding of groundwater ecosystems. He actively engages with regional and district councils throughout New Zealand who have the responsibility for managing groundwater resources. After Murray's presentation, there will be time for questions. I know that a lot of you here are concerned about the proposed mining at Sam's Creek, and Murray is happy to answer questions about generalised matters, but he's not able to comment on potential issues from Siren Gold operations at Sam's Creek. So thank you for your understanding, and I'll pass over to Murray. Thank you, Murray.
Thanks very much, Abby. Kia ora. Okay, this is a great shot of the springs on a nice day, and they just look spectacular, and this is why I think we're all really interested in these, in the springs and their protection. So, as Abby said, I was appointed as an independent reviewer for particularly reviewing the monitoring and making some recommendations about future monitoring in the catchment. So the Te Waikoropupū Springs are the largest and clearest springs in New Zealand. Mean flows of 10,000 litres per second in the main spring and about 3,500 litres in the Fish Creek Springs. Very high clarity, median of about 77 metres, which is brilliant. And the water spends about 8 to 10 years in the marble aquifer before surfacing in the springs, and so it's very clear. It's been listed as a water of national importance for biodiversity. The nitrate levels are very low, but there's been concern about increasing levels over the past 20 years, and this is what's led to Environment Court application in 2021-22 and a Water Conservation Order being granted, which came into force in October 2023. So one of the recommendations was that an independent review of the monitoring program be undertaken with recommendations for the future monitoring program. I wasn't involved in anything to do with the Water Conservation Order, so therefore was regarded as independent. And one of the other things that was emphasised in the Environment Court was the need for monitoring to provide early warning of changes in up-catchment water quality that might impact the springs. Because once you see something in the springs, it's a bit late. So what I'm going to do tonight is go through the process that I did for the review, look at the analytical methods and the laboratories that have been involved in monitoring or carrying out the analysis for the monitoring, and then focus on the future monitoring program, looking at the goals and criteria for that monitoring, the selection process for sites and parameters to analyse for, and then go through how I came up with the proposed monitoring sites and some summary comments. So the process for review. Last year I made 2 trips up to Tākaka. The first in July to basically get familiar with the catchment, to talk to as many people as I could and get aware of issues there. And then I followed that up with another visit in October where I basically presented the draft ideas that I had and got feedback, and then incorporated that feedback into a report which I gave to the District Council just before Christmas. Subsequently, I made a presentation to the District Council in February, where they were considering the proposed monitoring, and they, I'm pleased to say, have accepted the recommendations, and so the monitoring program is being implemented. And in fact, Joseph and Tessa are carrying out the first round of that monitoring over this week, which is great. For both of those visits, I was accompanied by Joseph, which was great. He has an extensive knowledge of the catchment and also introduced me to a whole bunch of people. I talked with many groups and benefited greatly from their knowledge of both the catchment and the issues. So TDC staff, community board, iwi farmers, flag members, Friends of Golden Bay, cavers, and on the second occasion I talked with Kevin as well, so that was great. I also read through many reports, and particularly the reports or the material from the Environment Court hearing. In addition to that, I had useful discussions with other researchers who'd been doing work in the Taka catchment, such as Andrew Fenimore, Roger Young, Mike Stewart, Hervé Morgenstern, and the laboratory managers Craig Radford from Hills Laboratory and Magali Moreau from GNS. So, I did what I could in terms of talking to everyone and considering all of those things, which were, I think, really useful as far as I was concerned anyway. So looking at the analytical methods, the main spring has been analysed the most extensively of any site. It's had 5 samples collected in the 1970s, and then regular monitoring started in 1990. And initially was every quarter, and then more recently it's been every month. A point that needs to be considered is, particularly with a long period of monitoring, is that methods have evolved and improved over time, and that is something you would expect and something that's good laboratory practice. And it is relevant here. We'll get to that in a minute. The main methods have been ion chromatography and cadmium reduction with colorimetric detection. Hill Labs have used cadmium reduction for low levels of nitrate, and GNS has used ion chromatography. 2 methods. Initially the regular method, well, they have 2 methods. A regular method which has a detection limit of 0.01 milligrams of nitrogen per litre. And then in 2018 they started using the low level method which has a detection limit of 0.003. TDC has collected replicate samples from the main spring since 2018, and it's been measured using 3 methods. The 2 main methods with GNS with the low level ion chromatography and Hill Labs with the cadmium reduction. They also used another method they've got, which was the regular ion chromatography, which they typically use for much higher nitrogen levels. They found there's no significant difference between the GNS low-level ion chromatography and the Hill Lab cadmium reduction. There was a difference, a significant difference between the 2 Hill Laboratory methods, but then the regular IC method wasn't used for monitoring. It was just used as the comparison. So I don't think that's particularly relevant. I think the key point is there's no difference between the methods that are being used for monitoring nitrate in the springs and the rest of the catchment, so we can have some good confidence. We've only had replicate samples since 2018, so we can be less confident about what happened before that, but that gives us a good indication of what's happening at the moment. Future monitoring program. First of all, I looked at the goals that we wanted to have for the program. Obviously, the first goal is to enable compliance with the Environment Court directives, to make sure that the running averages, the medians can be calculated. We want to provide early warning of up-catchment changes in water quality. As we just sort of talked about in terms of the methods and the laboratories, we want to ensure, I guess, that the monitoring results are robust. And there was also quite a lot of discussion in the hearings about different models and the models, the different assumptions that the models had. And those different assumptions provided different outcomes in terms of the model predictions. And what a good goal for the future monitoring program would be to provide high quality data from key land uses in the recharge area that will enable those assumptions to be actually tested for the models. That will enable much better constraints for both the hydrology, the flow and the water quality models that can then assist with the management. So in terms of the criteria, the first couple of criteria are common to any monitoring program. You need easy and safe access for sampling, you want good cooperation from landowners, and you want the ability to collect high quality samples. And by high quality I mean if you're collecting samples from a well, you want to make sure that it's not going to be contaminated by any surface contamination running into that well. You want to make sure that it's a good wellhead protection. Another aspect of high quality is that you want to be able to not only take a sample of the water, but you need to be able to get some idea of the quantity. So for a groundwater sample, you want to be able to measure the water level. For surface water sample, you want to have some idea of the flow. So I think both those things are inherent in the high quality. Oops, what did I do there? The next 3 points are more specific to Takaka. You want that the site can be sampled throughout the year with minimal dry periods if possible. In the karst environment that we've got here, you often get streams that will suddenly go dry as they go underground to feed spring or cave systems, and then that water can flow back up. For a monitoring program, ideally you would have minimal dry periods in that. Also, one of the goals was to actually get a good idea of what water quality was like for particular land uses and sources in the catchment. So the implication of that is that the sources of the water need to be reasonably well understood, and that the water sample provides some information for at least one of those goals that we had previously. And if all of those things are met, then existing sites with historical data would be an advantage because you've then got a longer time period to assess. So the plan is to sample all the sites monthly for a year, and then to review the frequency, but also to review the sites in terms of are they actually in the right place, getting the right sort of stuff. The first sampling occasion would be analysed for a comprehensive suite of samples. This will provide a good overall context for interpretation. It'll also provide a baseline for consideration of future land uses, and I think this is an aspect that's probably very relevant to the Siren Gold discussion, perhaps a bit later on. And then subsequent samples for the rest of the 11 months would be analysed for a more focused suite of parameters. So the full set, a group of field measurements which also provide the quantity information, the groundwater level or the flow. Then a suite of nutrients, they are the key reason for monitoring for the springs, the nitrates, phosphorus, carbon. And then a suite of major ions. It's been observed that the flow in the spring, as the flow increases and decreases, the values of the major ions also go up and down, and the ratios change as well. So the major ions provide information both on the mixing and also provides constraints for modelling. Then there's a big suite of heavy or trace metals. They're all expected to be low as it's an oxic environment in the groundwater. And when I was putting this together during the middle of last year, on the basis of our discussions, we decided to, or I should say Joseph decided to put in arsenic into the suite of groundwater wells that were being monitored in September, October. And I think 6 or 8 wells were sampled at that time. This was for the joint ESR TDC project on stygofauna, and so they also did arsenic, iron and manganese in those samples, and all of the arsenic samples were less than the detection limit, which was expected because of the oxic environment. But it does provide a good baseline for the future. And the last set of parameters are the age and source isotopes. O18 for, it gives you an idea where the source of it is. The oxygen 18 varies with temperature and therefore the altitude of precipitation. And so that gives you a really good idea in terms of whether the rainfall's been at the top of a mountain or in the valley floor. And the tritium is an age dating thing. So that's the full set that's going to take place for the first month. Subsequently, what I've highlighted in red, they are the parameters specified in the Environment Court Order: dissolved oxygen, nitrate and dissolved reactive phosphorus. There's also clarity, which there is already a separate contract with NIWA to actually provide continual monitoring of clarity over the summer months. Most of what is being taken out in the reduced set is the heavy metals, because they're expected to be low, so they'll keep in iron and manganese, but not the rest of them. As I said, the council accepted the recommendation and is basically putting those into account. Just in terms of the analytical costs of this, it's around about $60,000 for the first year. So there's a significant input of resource to get the monitoring going. Oh yeah, that's just the analytical cost. It doesn't also take into account the staff time and getting sampling sites ready. Okay, just move now into the selection of monitoring sites. And what I was really after was looking at what impact the upgradient land uses might have on water quality, in particular water quality in the springs. And so therefore I was focused on the recharge area, which is this purple dashed line here, which then extends down here and outside the square to the west and the south. And so I was looking for a coverage of different sources and land uses within that recharge area. So we've got 3 sites up here in the springs in blue. The blue signifies it comes from the Marble Aquifer. The orange down here signifies the Tākaka Gravel Aquifer, and then there's some red points here which signify the Tākaka Limestone Aquifer. The rivers are in green, and there are 3 black points here which I considered and then omitted for various reasons which I'll cover shortly. So the 3 river sites, we've got the Wanaro at Hanging Rock, and that basically gives an idea of the water quality that's coming out of the Western Hills. There's Tākaka at Harwoods down here, which gives an idea of the water quality that's coming out of the Southern and Western Hills, and Tākaka at Lindsay's Bridge. And that's a useful site because it's just above where the Tākaka loses a lot of its water to the Marble Aquifer. So zooming in a bit more on the wells, I'll start right over here in the wanting to get a really good idea of the water quality coming out of the upland marble to the east. Originally I was looking at Spittal Spring and Green Barra Spring, but usually the water flows sort of from the north. Sorry, I'll use this thing again. The north here, Gorge Creek, and then comes out in these springs down there. But talking with some of the caving people in the caving community, they indicated that although that's happening most of the time, probably 80-90% of the time, when the Tākaka River is in flood, the relative water levels can reverse and the flow can go backwards. And so the flow from the Tākaka River can then come into the lower cave and spring systems. And I wasn't sure, or no one was sure, how long that effect was in terms of the flooded Tākaka River water being in those lower springs. So for that reason I eliminated the Spittal Spring and Green Barra Cave as sources for that. Also looking at the source of this one, this is very affected, this well is very affected by the Tākaka River as well, so that was a mixed groundwater, river water source as well, so eliminated that. What I've chosen is these 2 dots here, the Gorge Creek water supply and the Ironstone Creek water supply, which are basically continuing flowing, but you're very sure that the source is from the upland water. So I think we'll get some very good indications of water quality relating to the upland marble. Now, coming over to the other side, we're sampling this well here in the Tākaka Gravel, which is east of the Wanaro River, and that basically gives an idea of land use in this area east of the river here. There's a couple of sites here, one in the marble, one in the gravel, which give an idea of water quality in this sort of general area in the valley floor. This is also in the marble, but it's very close to the quarry, and it was observed, or was noted in the hearings that the concentrations were a bit higher in the nitrate, excuse me, and likely related to the nitrogen explosives used in the quarrying operations. So we want to keep that well to just keep an eye on what's happening with that situation. And then as we come a little bit further over, there's these 3 wells here which give an indication of land use east of the Tākia River. Their nitrate concentrations are very much similar, so we've decided to select one of those wells. And likewise here, the 2 wells in the Tākia limestone are very similar nitrate levels, and we've decided to select one of those. And then there's also a well right up here in the Tākia gravels, which give an idea of the land use in that sort of upper Tākia area. So that was the sort of process I went through in terms of selecting the sites, and it ended up with 15 proposed sites, 3 springs, 3 rivers, the 2 creeks which give an idea of the upland marble, and then 7 wells in the valley floor in the different aquifers. And the other thing I just wanted to show, which relates particularly to the water quality coming out of the forested catchments. This is for the 3 rivers. We've got the Tākia River at Harwoods, and the orange is the total nitrogen, or it's basically includes the organic nitrogen, and the blue dots are the nitrate nitrogen. And you can see that coming out of forest catchments, most of the nitrogen is in the organic form. And in fact, the ratio or the average ratio between the medians is a factor of 10. When you go to the Winara River, there's a much smaller data set, but the organic nitrogen content is still a lot higher than the nitrate content. The factor is about 3, I think it is. And for the Tākia River at Lindsay's, the factor is about 2. So what's happened here is we've got the x-axis is, the y-axis is much different. This is up to 0.9, whereas the other one's 0.3. So there's been some input of nitrate from the farming in the valley floor, and that's been largely as a nitrate rather than organic nitrogen. The relevance of this, I guess, is that when the water goes from the rivers into the aquifer, it's an oxygenated aquifer, and by the time it's spent 8 years in that aquifer, all of that organic nitrogen has been converted to nitrate. So you need to have an understanding of not just the nitrate in the catchment, but also the various forms that it takes in the different places. So we're making sure that we have organic nitrogen measured, and also having both of those sites, I think, will be valuable as well. That's about it. There's a couple of further comments. The full report to TDC is on their website. There's one section in the report that came out of, I guess, the conversations that I had with people in terms of things that were outside the scope of a regular monitoring program, but that would be really useful in terms of either understanding the processes, interpreting the results, those sorts of things. So the first bullet point I got, and it's not an exhaustive list of what's there, but a better understanding of cave and flow in spring flow paths and dynamics. Specific monitoring for farming practices. The monitoring for seeing what happens to a farming practice needs to be much, I guess, more immediate, close to what's happening actually on the farm. The impacts of gorse and broom in the catchment. They fix nitrogen, and most of the work's been done in the Rotorua catchments for that, but they can fix quite a significant amount of nitrate. Not sure what happens here at Takaka, but there are a couple of ideas that could be looked at in terms of getting an idea of what that impact is. GNS have got a new groundwater research program, and one of the sites that they're looking at in that program is in Takaka here, so there'll be some additional benefit, some synergies with that new program. They're doing some additional tritium analysis and some additional isotopes, which will also feed into our understanding here. Joseph's previously carried out some synoptic surveys whereby he's just gone out and sampled every well he could possibly do, which gives a really good idea of what spatial groundwater quality is like in the catchment. These were carried out in 2006 and 2016, so repeat of those would also add to the picture of water quality in the Takaka catchment. Finally, I was asked to comment in terms of who should carry out the monitoring. In my view, TDC is the agency with responsibility for implementing the Water Conservation Order. It has access to all sites and has good relationships with landowners, trained and qualified staff. It's obtained the required funding for monitoring the sites and reports and disseminates the results to the public. So therefore, in my view, TDC should be responsible for carrying out the monitoring program, and they've started to do that. Any questions?
On your slide when it showed the organic nitrate or total nitrogen and the nitrate, and you said it's converted within the Marble aquifer.
Yeah.
Is it a one-to-one conversion? Or is it
Yep. Because all those units are in terms of nitrogen.
Yeah.
So and most environmental scientists work in terms of nitrogen, which means you can convert from ammonia to nitrate to nitrite to organic nitrogen, and it's all the same unit. It's all expressed as N, yeah. So, I mean, the levels in the springs, for example, are between 0.3 and 0.5 historically. So let me back up to that slide. The Taka at Harwood's, for example, I mean, the maximum thing we've got here is 0.3. Most of the concentrations here are a bit lower. Most of the concentrations at Lindsay's Bridge between, 0.1 and 0.3. So this is some of the information in terms of where the various concentrations come from. And so even though we're talking about the organic load being high relative to the nitrate, it's still lower than the values we see in the springs. Yeah. Because the y-axis, most of those values are below 0.3.
Well, you've got that slide on. How do you explain this spike in 2000 for nitrate N? And something must have gone on there.
I don't know I don't know anything about. I've just been given those data. I don't know anything about how they were collected. I don't know about what the flows were or anything. But with the river, I mean, there is quite a lot of the variability is associated with flow because the rivers, do go up and down with rainfall and those sorts of things.
But stream outliers that don't fit the general trend, and you just ignore those, or how do you deal with those?
For those data, it's probably not the best person to talk about it because I'd need to look at what's happening with the flow in the rivers and try and understand what the relationship is with those first.
I have a series of questions. Andrew, we've been, Friends of Golden Bay has been sampling the springs. I might add, not monthly, but always at least fortnightly for the last 9 years, both springs, Main Spring and Fish Spring. Mm-hmm. There is, on the basis of the information we've gathered, around about 350,000 bucks worth of nitrogen as urea input floating out to sea from those two springs every year. And there's probably around about half as much again going out through undersea vents, according to the best model that we have. So around about $500,000 worth every year from probably a dozen farms in the catchment. This would be probably the farmer's best reason for wanting to keep that under control, reduce it slightly. So,
is that a question or a statement?
Sorry?
Is that a question or a statement? Because it's an incorrect statement.
Let's let him finish his
question.
Yeah.
So, my question around it really, I'm really glad to see organic nitrogen being included in sampling at the rivers that come into the valley.
Yep.
Urea is also an organic form of nitrogen. It's about just under 50%. The dissolved organic matter in the rivers would be about 3% nitrogen, as typical for humates and fulvates. And has there been any work done on where and by what pathways the urea, which presumably sinks into the ground, ends up as nitrate in the aquifer?
I don't know about here, but certainly in other places, the urea does transform pretty quickly into other forms of nitrogen, particularly ammonia and nitrate. And we're going to be analysing the groundwaters for the organic nitrogen, which will pick up the urea if it's there. Generally speaking, by the time you've got down into the aquifer, the urea, the mobile form of, or the mobilised form of nitrogen is the nitrate, and it's the nitrate that actually goes, that is the mobile thing that goes through. So I would expect it'll be mostly greater than 90% nitrate by the time it gets into the groundwater.
So it's oxidised on the way down to the groundwater.
Yep. Most of it happens in the soil. Yeah.
Right. Yeah. So to take it a little further, Friends Golden Bay has established that actually it was because of work that we did and running samples, check samples, that the GNS lab developed their low nitrate method, which we're very pleased to see, and it really has increased the quality of the reporting. So we're getting good information on what comes out of the aquifer. I'm wondering whether that could somehow be combined in farmers' hands, I don't want to know about the details, with the information that they have on their farms about what they think they're losing into it. Because if you can monitor the inputs and the outputs of an unknown process, that gives you real insight onto what's going on within. Can you comment on that, please?
That's sort of outside the scope of the monitoring thing, but there is I'm probably the wrong person to answer this. I had some discussions with GNS about that, who do basically the nitrate's got the nitrogen molecules as well as the oxygen molecules, and you can do isotope testing on both of those things. And so we looked, was it worthwhile looking at the nitrogen isotopes for that? The two sources, or two main sources of nitrogen in the catchment, have actually fairly similar sort of signatures, and so it would be fairly difficult to use the nitrogen isotope and the oxygen isotope in the nitrate to actually distinguish that. Mike Stewart, who's at GNS, is very keen on doing something about this. There's not enough data, basically, at the moment to actually tease that apart, but that's one of the sort of things he's hoping to do as part of this new GNS research program, to actually do some more work in Tākaka on those nitrogen and oxygen isotopes of nitrate. Yeah. The broad discussion indicated that it was still very much we haven't got enough data, it's a very research sort of orientated thing as opposed to a monitoring thing, which you know what the source would be. Yeah.
Could you say something about the transmission and the different pathways through which arsenic, and the types in which arsenic changes in water? And while on the topic, zinc and lead as well, for example, as heavy metals. You've mentioned those.
Yep. We've done some research in Canterbury where we've looked at arsenic and... Did we do lead? We did lead in column experiments and we did zinc in column experiments. We had a research program where we were basically trying to get rid of nitrate in a shallow oxygenated aquifer, which is Canterbury, basically. So the concentrations we were dealing with down there were about 7 parts per million. And what we did was we put a wall across the groundwater flow path. We filled that wall with a mixture of gravel and wood chips, so a good carbon source. And then the groundwater flowed through that wall. It became very reduced. It got rid of the oxygen first, and then got rid of the nitrate. Canterbury gravels had quite a lot of arsenic associated with them, and so if you make the groundwater reduced, that mobilises the arsenic, and so we had a little spike of arsenic, which we could follow because we had our monitoring arrays, and it basically went 40 metres downstream of the water, and then there was enough mixing with surrounding groundwater, which is oxygenated, and it didn't go any further than that. So beyond 40 metres, it was less detection limit. So very much the transport of arsenic was conditional on being reduced groundwater. So if you had oxygen in the groundwater, it basically precipitated out, which is reasonably relevant to the Tākaka situation where you've got oxygenated groundwaters. So, which is why I wasn't surprised for all the arsenic results we've got so far are all less than detection limit because you've got oxygenated groundwater. For the zinc and the lead, they tend to be less mobile than the arsenic, and it basically either has to be acidic groundwater or very reduced groundwater to get any movement. They were in column studies, which we have published here. So they've still got that relevance here. And that's probably also the situation here, as you've also got quite a store of carbonate in your marble aquifer, so that will tend to keep the pH slightly below 7, which is good, protective of you.
In your Canterbury example, do you have any idea of what the total weight of arsenic was that was affected by your experiment?
No. Partly because it was difficult to get a really good estimate of the flow through the wall.
Yeah.
In terms of the concentrations, when we first put the wood chip into the aquifer, there was a sort of a burst of labile carbon that came out of the wood chips, and then it settled down. So we had a burst of about four months, and we had some mobilisation of arsenic during that 4 months, and the maximum it went is 40-50 metres. The maximum concentration we had of the arsenic was about no, I need to go back and check. It was slightly above the drinking water standard, but it only was there for that first few months of operation, and it only went for 40 metres before it precipitated out here.
Thank you.
That's okay.
I don't want to hold everyone up anymore.
It's all right. Are there any other questions? Everyone at the back?
Right. Yeah.
A question around the quarrying. Have you seen any other examples across the country with quarrying and nitrogen and pathways or how it can enter into groundwater systems? Have you got any other examples you could share around? Just because it is quite high relative to this catchment.
Yeah, I haven't myself, but I do know they use nitrogen-based explosives, and the well is sort of immediately down gradient of the quarry, and it seems a very plausible link. Yeah, but I haven't looked for those sort of examples here.
Well, if there are no other questions, we might bring the formal part to a close.